All right. Hi, everybody.
Hi.
So, we have been talking about these statistical tests, right? That's what we've been working on. You guys had finished up the t-test section. For the most part, that was kind of like the same idea over again. I just don't think we got to the example where you're given data instead of statistics, right? It's basically all the procedures the same. You're just going to put in your calculator a little bit differently, but everything conceptually was identical, right? You guys went through that second half of the slideshow to look at what's going on. If there's questions on any of that stuff? So far, so good? Okay. Today, we're going to push ahead then and start talking about our next type of statistical test. There'll be 3 statistical tests we'll look at in this chapter. So there's the t-test, check, we've done that. There's the chi-squared goodness of fit test, that's what we're going to talk about today. And then there's a chi-squared test for independence, that'll be what we'll talk about next time. We still need to do a quiz for this chapter, and we have an activity for this chapter, and we'll have a test for this chapter. All that stuff won't happen until after the thingamajigger conference, the conference and stuff. It won't happen until next week. And I'm not even sure I really want to do the quiz or the test next week, or the quiz or anything even next week. I'd rather just get the activity done and do some more practice. The hardest part about this chapter will typically be deciding which test you're supposed to use for the situation. That's typically the hardest part. So I'd rather just get through the 3 types of tests and then settle in for a day where we can talk about which one should you use? How would I know? Everybody good? So we'll do this today. This is probably 50-ish minutes. This presentation. After that, we're going to just stop and give you guys individual time if you have to talk to me about your IA stuff. A lot of us sent in ideas for topics, and I sent it back as oh, that won't work for this reason or that reason or the other. It's already taken, or well, you're close to something here, but I think we need to talk about it some more, or this, that, and the other thing. So I'm going to leave the last half of class available, so if you have IA stuff that you need to talk through with me about, get a better idea of what you should be doing, or finding a topic and settling in on something, I'd like to do that. Sound good? Okay. All right. So today, goodness of fit tests. That's what we're talking about. So, the idea here for a goodness of fit test is sometimes you want to test to see how well one set of categorical variables match up to a known standard. So let's say that you have your student grade level and your performance on some sort of standardized test, right? And for the sake of argument, let's say it's a PSAT that's given as a percentile grade. So you have your school, and you want to see how well the students at your school are doing against the national average for each of those. So one way you could do that is you could test each grade level separately using a t-test, or you can do your school as a bulk doing this chi-squared test for independence. And that's kind of what we're doing what we'll be talking about right now. The chi-squared goodness of fit test. The other option that we'll talk about next time is the chi-squared test for independence. And that's where we're going to look at testing to see if 2 variables have an association with each other, kind of like a cause and effect relationship. but that'll be for next time. So for today, the example that we're going to kind of work through is just going to be this idea of M&M. So we're going to keep referring back to this idea over and over and over again as we kind of talk through what this goodness of fit test is doing and how it works and how to perform it. That's going to be the gist of it. Everybody okay? All right, so here's the situation. Mars Incorporated makes milk chocolate candies. The company's customer affairs department says the color distribution for candies is 13% brown and red, 14% yellow, 16% green, 20% orange, and 24% blues. That's what the company is advertising. So they make just like a giant vat of these M&Ms. They dump in all these colors at a different ratio, they mix them up, and then like a machine dumps out like some number of them into the bag, and the bags get sealed and off they go to the customers, right? What you want to do is it's like, okay, well, I went out to the store and I bought myself a bag of M&Ms. I want to test to see how well their mixer is doing, right? If their mixer is doing well, the ratio of colors in my bag should be pretty close to this if they've done a good job mixing them. If they haven't, or the color ratios that they're advertising of making, that's not exactly what they're doing, I should be able to see that in my sample, or I should be able to test for that in my sample. Everybody's okay? So that's what we're going to be doing, is we took a sample, some bag of M&Ms, we counted up the colors that we see below, and we want to test to see if, like, does that distribution match their advertising. If it doesn't match, there's probably one or two things going on. Either they're not mixing their colors up well enough so that they're getting, like, you know, a good random assortment, or they're just not making the colors in the distribution that they're advertising. Okay? So, moving on. So, for example, here, if we look at what we observed when we got our bag from the store, we got 9 out of 60 of our M&Ms were blue. That would imply that like 15% of our bag was blue. But advertised, it says 24% of the M&Ms they make are supposed to be blue. You expect, you know, maybe 24% in the bag to be blue or something close to that. Is 15% close enough to 24% to say that, like, we just got like kind of a weird sample, or is this like, you know, like how close is close enough? That's really what we want to be able to do. That's what we're going to be doing this chi-square test for. So with just looking at the blues, you could do a t-test for the blue, for just blues. Or the null hypothesis is that the percentile of, or the percentage of blue should be 24%, and the alternative is that it's not 24%. And then we could do that t-test, and then we'd have to do it again for oranges, and then for greens, and then for yellows, and then for reds, and then for browns, to see if any of them don't really match. Is everybody okay with that? That seems like a lot of work. That's 1, 2, 3, 4, 5, 6 t-tests I'd have to do separately. Yuckarooskies. The alternative would be to use a chi-squared goodness of fit test that we're going to talk about now, where I can do the whole distribution of colors with one test. Okay? So the chi-squared goodness of fit test and the t-test setups are going to sound pretty similar, but if it seems like, oh boy, I'm going to have to do like 5 or 6 t-tests here to figure this out, we probably just want to do one goodness of fit test. Right? That's much more efficient. So just like the t-test, we start with a null hypothesis. And the null hypothesis just is that your sample is a good fit to the known distribution, the advertised probabilities. So in our case, that the color distribution for M&Ms is correct, i.e. that it matches the company's distribution, and we put matches and correct in quotation because we don't really specify what that means. But really what we're saying is that the probability that our sample came from a collection that had this percentages as advertised, the probability is pretty high that I could have pulled that sample from that kind of stuff. That's what we mean by correct or matches. The alternative is simply that the color distributions is not correct, that it does not match the advertised distribution. Okay? All chi-squared tests of goodness of fit, the null is going to be the sample distribution matches the known distribution, and the alternative is that it does not match the known distribution. Okay? Everybody's cool with that? So they're all going to sound kind of the same. You're just going to input whatever it is we're talking about, whether it's M&Ms or dog breeds or grade levels of students or whatever the categorical variable is. So alternatively, you could write these hypotheses symbolically as well. So if I wanted to do this symbolically, the null hypothesis is the probability of blue is 24, probability of orange is 20, the probability of green is 16, and so on and so forth. And the alternative is at least one of those probabilities is incorrect. Now, in reality, are we going to want to do this in words or in symbols? I mean, you probably want to do it in words. That feels like a lot less writing than all these symbols that we just wrote down here, right? Especially because it's the verbiage is kind of identical every single time. Just that, like, the sample matches the sample distribution matches the known distribution. And you just have to say of what's. You know what I mean? So once we've written our null and alternative hypothesis, we need to compare the observed counts to the expected counts. Now the observed counts, that's what we have back here, where I counted 9 blues and 8 oranges and 12 greens. That's me opening up my bag of M&Ms, separating out the colors and counting how many of each color I got. That's my observed count. The expected count is, hey, I had a bag with 60 M&Ms, and 24% of them are supposed to be blue. How many blue ones would I expect to have gotten out of that bag? How many orange ones would I have expected to get out of that bag, and so on. So that's what we mean by expected counts. So again, if 24% of the M&Ms are supposed to be blue, and I had 60 M&Ms, I just multiply 0.24 by 60, and I get 14.4.
I'm sorry, in my computer, would the DF then be 6? Because there's 6.
We'll get to the
Okay.
we'll get to what degrees of freedom means in a moment. Yep. So 0.24 times 60 gives us, we'd expect 14.4 blue M&Ms, right? Is it okay that it's a decimal? Yeah, expected counts can certainly be decimals. Obviously, you can't get 14.4 blue M&Ms, but that's not saying that's what we measured. That's saying what we'd expect. Expectation can certainly be decimals, even if it makes doesn't make sense in context, right? It's fine to be decimals. It's like saying the average American family has 1.5 children, right? Like, we're not talking about everybody, we're just talking about on average. Next question. So if I do that for each of the 6 categories, these are my expected counts. And then if I collect that into a table and with my observed counts, how does it look? How different are those look? That's basically the question. I don't know, they look kind of different. Are they different enough to say that we got that they actually come from a different distribution of colors? I don't know. They look a little different. Are they different enough? That's what we're going to be trying to ascertain. So another way to visualize this is, here's like a side-by-side bar graph where I have observed and expected counts, and like, okay, that looks some of these look pretty different, right? Blue and yellows in particular look pretty far apart. Maybe, I don't know. So to make a decision about, like, are these distributions different enough we're gonna do this chi-squared statistic, and the way we calculate this is we're gonna look at each observed count minus its expected count squared divided by its expected. We're gonna add that up for each category. So we're gonna do this calculation for blues, and then reds, and then yellows, and then oranges, and for all 6 of them. And then we'll add those all up, and that'll give us a chi-squared statistic. So here we go. There's my observed and my expected counts. This is me performing this chi-squared computation. Notice if there's just 6 categories, it's not so bad to do this by hand, right? This is a calculation that I would expect you to be able to do by hand if I asked you to do it on a test. We'll show the calculator can do it also, but if assuming the number of categories is relatively small, this is something I would expect you to be able to show the work for. Which again, like, that's not so bad. 6 fractions to make, that's not the end of the world. That's totally doable on a calculator. Everybody's okay? So we grind that out and we get 10.180 as our chi-squared statistic. So essentially what this chi-squared statistic is doing is it's basically describing the distance of the observed counts from the expected counts. So the bigger your value of chi-squared, probably the bigger the differences between the observed and the expected, or the larger kind of the deviation away from what we'd expect. So this would be the bigger that chi-squared gets, the better evidence you have against the null hypothesis. And then, but the question is like, okay, you said big values of chi-squared. What the heck means big, right? Like, is 10 a big number? Or is that a small number? If you usually get like numbers less than 1, 10's pretty big. If we're used to getting numbers in the thousands, 10's pretty small. Like, you're not giving me a scale to judge how big the number 10 is. You know what I'm saying? You know, like, if you have 10 cars, that's a big number. You know, if you have, 10 shirts, it's not a very big number, right? So it just kind of depends here a little bit. And let's talk about how we get that. So the way we're going to do this is we're going to look at kind of the same way we did for the t-test. So we're going to use that chi-squared statistic to calculate a probability. So just like when we did the t-test, we got that t-statistic, and then we looked at the t-distribution and found where that t-value was and looked at the area under the curve either before or after the value of t, or in some cases at each end. We're going to do the same kind of thing here with the chi-squared distribution. The difference is that there are infinitely many different chi-squared distributions. And the type of chi-squared distribution is going to depend on the number of categorical variables, essentially the number of choices we have for categorical variables. We call that the degrees of freedom. So the degrees of freedom are going to describe the shape of your chi-squared distribution. To you guys, that's going to mean basically nothing other than a number on a sheet of paper when we ask for the degrees of freedom. If you hit the draw option when you do the chi-squared distribution, is the only time you'll see any difference between like 3 degrees of freedom and 5 degrees of freedom, because the shape of the curve that it draws would look a little bit different. But that's essentially the only thing that can change. So pictorially, the graph here on the left, I guess it's your right, shows the chi-squared distribution with different degrees of freedom. So that purpley curve is for 1 degree of freedom, the red curve is for 4, the green curve is for 8. So again, the number of degrees of freedom are going to just dictate the shape of that chi-squared distribution, which to you doesn't mean anything because you're never going to be calculating the p-values by hand. The calculator will do that for you. But you may notice if you select the draw option on the chi-squared test that what the graph that the calculator draws might look different in different problems. That's the only reason why. Everybody good? So the degrees of freedom you can calculate by just looking at the number of categories minus 1. So let me explain why there's a minus 1 there. So in this problem, we're talking about these colors of M&Ms, right? We have 6 different colors. I tell you to pick a color. How many choices do you have for choosing that first color? 6. So you've made one choice. You picked a color. How many choices do you have for the second one? 5. And then we've chosen 2 colors. How many choices are left for the third? 4. And now the fourth, 3, and the fifth, 2, and the last one. Well, if you have only one thing to choose, is there really a choice there? No. So you could make 1, 2, 3, 4, 5 decisions, and after that, the choice is made for you. That's why it's the number of categories minus 1, right? So every time you pick a category, you get to the last spot, there's only one thing left, and there's no choice left. Does that make sense as to why the degrees of freedom is just the number of categories minus 1? That's essentially all we're saying. Now, before you can do a chi-squared calculation, even before you would want to write your null and alternative hypothesis, you need to check 2 conditions for that result of your chi-squared test to be valid, for you to be able to say anything about the result. The 2 conditions are the randomness condition, that is that your sample that you're taking isn't too big, doesn't contain too much of the population. And the second is that your expected counts are all greater than 5. That's called the large counts condition. So there's 2 things that we need to check beforehand. And we'll circle back and talk about those in detail in a moment. So you've checked your 2 conditions. You've written a null and alternative hypothesis. You've computed a chi-squared statistic. You've used that chi-squared statistic now to check whether we think that these are a good match or not. The way we'll do that is comparing the chi-squared statistic or a p-value against the level of significance, right? So this is that same alpha that we talked about for the t-test. It's the same idea. So depending on what you're testing, your tolerance for a mistake may be higher in some situations than in others. In situations where if you made a mistake, it doesn't really cost too much, a level of significance can be kind of high, could be 5, 10, 15%. Probably doesn't matter when we're talking about the distribution of colors in M&Ms, right? Like nobody's life is at stake there. If it's like, oh yeah, I think these are really different, and it turns out you just got like a really low probability bad sample, and the things were the same, nobody's dying because of that, right? Now, if you're doing medical testing, there the level of significance you probably want is much, much lower because somebody's health or well-being or potentially their life is at stake due to that, right? Everybody's okay? So, you'll use this level of significance to do one of 2 things. The first is you can create a chi-squared critical value to use to compare against your chi-squared statistic. Okay? So the idea here is you have some chi-squared distribution, right? Let's say we have some level of significance, let's say it's 5%. So that shaded area under the curve represents 5% of the area under the curve, right? This value here is your chi-squared critical value, the x value that is the boundary there. Everybody's okay with that? So if your chi-squared calculated value lives to the right of that, if it's bigger than the chi-squared critical, you found an absurdly unusual sample, right? Now, your sample could be unusual just because you got lousy luck, but the odds are pretty bad that you'd be that unlucky. The more likely situation is that the distribution you sampled from was different than the advertised distribution, right? So this is the same thing we did with comparing P and alpha. It's just another way of doing it. Is everybody okay with the picture that I've drawn here? Does that make sense as to what we're doing? Because if we look at, if we took the corresponding p-value from here, you'd have like p is less than alpha, or we'd have chi-squared calculated greater than chi-squared critical. Right? They're equivalent statements. It's the same thing, right? So depending on what information is given to you, you use what you got, right? For the most part, you'll be given this level of significance, and if you're given a chi-squared critical value, that's fine. You can use it to compare the chi-squared calculated value to it, which you could do if a calculator was not allowed, but in this class you'll always have a calculator allowed to you. Or, since calculator is allowed, you could just take the level of significance attached to that chi-squared critical value and compare it to the p-value that's going to come out of your calculator anyway. So it's either way of doing it is fine. Go ahead. Does everybody feel okay? Okay, so this is the criteria here for accepting and rejecting the null and alternative hypothesis using the chi-squared critical value. So if chi-squared calculated is greater than the critical, you find evidence in support of the alternative or reject the null hypothesis. And if the chi-squared calculated is less than or equal to chi-squared critical, you found evidence in support of the null and would reject the alternative. And again, remember the null hypothesis is that the two distributions are good, that they match. All right. So this is the same picture that I just drew, right? So here we have our chi-squared calculated, the 10.18 that we calculated earlier. The shaded area under the curve is the p-value. This is the 5 degree of freedom chi-squared distribution. I went to my table to look up the critical value at 5% for a degree 5, or 5 degree of freedom chi-squared distribution. So that chi-squared critical value was 11.07. So when I did this as a student, you'd have to go and look this up out of a table. They have a table of values in the back of the book you just look up the critical value from. Nowadays you use a calculator, you do an inverse chi-squared and solve for the value, but it doesn't really matter. So we got 11.7, so we see that the chi-squared calculated is less than the chi-squared critical here. So we would find evidence in support of the null. The two distributions match. Everybody's okay? So again, just same picture we drew. Blah, 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 blah. The other way you can make the decision is you can compare the p-value with that level of significance, just like we did before for the t-test. So if your p-value is less than alpha, we find evidence in support of the alternative and reject the null. Or if p is greater than or equal to the alpha, we find evidence in support of the null and reject the alternative. Notice that the inequalities are going different directions for if you're doing chi-squared critical with chi-squared calculated versus p and alpha, right? the accept and reject null conditions, the inequalities are reversed for those things. Which should make sense with the picture I drew before, right? A big chi-squared critical, or big chi-squared calculated means a small p. A small chi-squared calculated means a big P. Okay, so we mentioned earlier that there were two conditions that we need to check before we can use our chi-squared statistic to say anything about, or to draw any conclusion from it. There's two things we need for that result to be valid. So the first condition is the randomness condition. So the data you sample from needs to be from a randomized experiment. So like, we'll assume drawing from the bag of M&Ms that the M&M Corporation stirred those M&Ms enough to where they're all mixed together randomly. Probably a fair expectation. And then the second part of the randomness condition is that your sample contains less than or equal to 10% of the total population. Okay? So let's assume that our sample was 60 M&Ms, right? If 60 M&Ms was 10% of the total population, how many M&Ms are there in the world then? 600, right? Now, how many M&Ms are there in the world? I don't know, but it sure as heck's more than 600. I've eaten 600 M&Ms in my life. I know there's got to be more than that. Everybody's cool? So that's how we kind of verify that, is you just figure out, okay, if it's 10%, what would the total population have to be? Well, the population has to be bigger than that because common sense dictates, or you're given it some way in the question where the actual population you're sampling from is. The second condition is the large counts condition. That just says that all the expected counts have to be greater than 5. So if we go back here and look at our expected counts, so I look at my expected counts, the smallest expected count on my list is 7.8, right? Is that bigger than 5? Yup. Do I have to compare all the expected counts to 5? No, man, I'm just going to compare the smallest one, right? If I know the smallest one is bigger than 5, then all the rest of them are. I really only need to check the smallest one. Everybody's cool? So again, like, it's okay to check them all. It's not wrong to do that, but like, you know, like I got better things to do than like write down greater than 5, greater than 5, greater than 5, you know, like, just give me the minimum expected count and let me check that one. Everybody feel good so far on what we're doing? We've looked at how to compute this, what conditions to check, how to write your hypotheses. So this is a summary now of how to do this test. So suppose the two conditions are met, our sample is less than or equal to 10% of the population, and all the expected counts are greater than 5. So we start by writing our null and alternative hypothesis. The null is always the sample distribution is a good fit to the known distribution. And the alternative is the stated, or the sample distribution is not a good fit to the known distribution. And then we find the expected counts for each categorical variable, and then calculate the chi-squared statistic using the formula we discussed earlier, and then compare that chi-squared value to a chi-squared critical value, or the calculated p-value compared against the level of significance. Does everybody feel good? Okay. That's it. That's the gist of it. Okay? We'll do the other half of the other chi-squared test next time. I'm stopping here so that if you have IA stuff that you still need to talk to me about, or you haven't even made a suggestion to send in and need to brainstorm a little bit, or I rejected what you thought, but you're like, I think this will work, and I'm still kind of stuck on it, and you want to talk to me some more and try to convince me that what you got is okay, or whatever. If you just need you're just like, I need some help me, that's fine too. Before we break to do that though, I'm not keeping that little doodle I drew on there because the next slide has basically the same doodle. I want to point out to you guys that if you go and look at our class page and you go all the way down to the announcements, there's an IA topics tab or announcement down there with a link. That's a link to a Google Doc that shows the IA topics people have already chosen or been rejected on. So if you're thinking of an idea and you're like, I wonder if this one's already been taken, you can click on that link and take a look and be like, oh shoot, Jeannie Smith already took my idea. Dang it. I have to think of a new one. Or, oh, I was gonna do this. Oh, Holly Jones already got denied on this one for some reason. So you can check. Yes, sir.
Before I said no, you go me saying that you need to find a way to find the information. Can we just find sources online to get it?
Yeah, if you can find a publicly available data set, for sure. I think and probably ChatGPT is a good way of hey, can you find me this data? Would be what I would probably go with rather than Google. I feel like you might get a better result from that. But yeah, ideally, when you're thinking about this, you want to think about getting your data collection either one of two ways. You can find it publicly available somewhere on the internet. Or two, something that you could collect via self-reporting from your peers. So if you can't get it one of those two ways, you probably don't want to do that topic, because that means you're going to have to find that data yourself or collect that data yourself, which means designing an experiment and measuring stuff, and it's going to stink to get a randomized sampling that way. That's rough, and I would encourage you against it because you're probably talking 50 hours of work just to get your data, not even to write anything. So I don't know what your free time schedule looks like. Mine would be, I would be sunk on that kind of thing. So if you're not sure, talk to me. I won't let anybody do that doesn't realize that's what they're kind of getting themselves into. So if you're suggesting something, I will make sure that you realize what it's going to entail if you're stuck on doing it. I won't let anybody go down that path that doesn't know that that's the path they're going to go down. And I would strongly encourage them to do something different because I don't think that's a successful path. Yes, Ethan?
You shared.
Oh, I don't have the permissions for you guys? Okay. All right, let's see, how do I do that? This is the thing. And then what do I do here?
Which idea?
Share, private to me, okay. Share, what do I want to do?
It's just like from the book, I think.
Oh, I just do this. Anybody in Notre Dame can do that. Okay, can you check for me out? Good? Perfect.
We email it to you still, right?
Yeah, when you have a topic idea, you for sure send the proposal via email, just like before. That part doesn't change.
And then it says it's being properly formatted. Where does it say on my the example?
So if you look at your OneNote,
Can I say that first?
yes, you may.
Spoken right. That's
And we look at the content library. If you look at the IA stuff at the top, it discusses in part 1 kind of what you need to have. And if you look at the thing underneath it, it talks about how to format your email to send to. Cool?
Yeah.
So those are the two things there.
Can we check mine? I just resent that right here.
Maybe? I'm gonna stop the recording though and sit down and as people wanna come up and talk to me. For sure, you can come up and talk and we can go through what you just sent me. That's totally fine. That's basically what the rest of the hour is though. If you got stuff to catch up on, go ahead and catch up. we don't have an IA topic.